Okay, so yesterday we were going over circular motion, okay, and we kind of went over the basics of circular motion, and that is for something to move in a circle, it's always doing what? It is always accelerating, even if in a uniform circle, which would be this kind of circle, okay, it's moving at a constant speed. Okay? Its velocity is not constant. The magnitude of the velocity is, okay, but the direction is obviously always changing because it's going in a circle, okay? And so as a result, it is always accelerating, and an acceleration requires a F-net, okay? In this unit, we call that F-net the centripetal force, okay? Or as it sounds, because it sounds so much classier in English, centripetal force. Okay, because it just, I don't know what it is about it, but it sounds classier. Okay, not like aluminium. Did I use that joke yesterday? No, I can remember if you guys are paired too. Okay, so yeah, it's so sometimes I'll say centripetal just because I remember and I remember how nice it sounds. Other times I'll say centripetal. Okay, but in the end, it is the net force that is pulling the object towards the center, because centripetal means center seeking. Okay, whereas centrifugal means center fleeing. And there really aren't any center fleeing forces, at least for a uniform circle. Okay? Now, that said, if that centripetal force suddenly vanishes, what will happen to the object? Right, it'll go in a straight line. Does it go directly out of the circle? No, it goes, what do we call it when it just touches a curve but doesn't cross it? Starts with a T. Tangent, yeah, okay. It will go tangent to the circle at the point where that centripetal force or centripetal force vanished, okay? Because now it's no longer being governed by Newton's second law because the net force is gone, and it's now being governed by Newton's first law, okay? Meaning it will go off at a tangent, okay? This is actually something that NASA uses all the time, okay, for gravity assist. Okay? When we want to send spacecraft to very distant places in the solar system, none of them can carry enough fuel to just have the engines on and go there. And so what they will often do is they will send them toward other planets in the solar system, have that planet's gravity pull it in, and then it'll go off at a different angle and pick up some speed using what they call the gravity assist. Okay? You may have seen it in The Martian. They used it to get back to Mars to rescue Mark Watney. Okay? They used Earth for a gravity assist, okay, and then shot themselves back to Mars. Okay, we do that all the time. When we want to send things to distant places, like for example, when they sent New Horizons out, they did a gravity assist at Jupiter. They did a gravity assist with Venus. Okay, so they sent it to Venus, it did a gravity assist, shot it to Jupiter, did another gravity assist, sent it on its way. Okay, so we kind of steal a little bit, but once that gravity, which is providing the centripetal force, weakens enough, the spacecraft can push off at a different angle. All right, yesterday we ended off with this formula here, okay? And we said that this formula is really just V equals d over t. Okay? And we do mean distance over time on this one, okay? Because obviously in a circle, the direction is always changing. Right, so this is calculating our centripetal speed, okay? And the distance is the circumference of the circle. What did big T stand for? Period, right, okay? And the period is the time for one cycle, circle, orbit, oscillation, okay? Whatever it is, it always means the time of one cycle, okay? All right, now, if we do that, okay, that means that as radius increases, okay, then what should happen to V? It should also increase. Okay? That is assuming T stays the same. But generally, if a circle gets bigger, does it take longer for you to go around it?
Yes.
Yeah. Okay? Now, this is kind of a weird thing because it happens with merry-go-rounds. We watched, the morons, motorcycles, and merry-go-rounds yesterday. Okay? If I'm on a merry-go-round, where do I have to hold on the hardest? Where would you be moving the fastest? On the outside. So where would you have to hold on the hardest?
Inside.
Outside. Because that's where you're going the fastest. That's where your inertia wants to leave the circle the most. If you're standing in the middle,
Oh, yeah.
you're actually not, I mean, sure, you're rotating, but you're not actually moving in a circle because your radius is what?
Small.
0 if you're at the center, yeah, really small. Okay? Yeah, so if I'm standing on the center of that merry-go-round, well, I might be turning around and around, I'm not moving in a circle. Okay? And so as a result, my centripetal speed would be 0, and my centripetal force, the force required to keep me there, would also be 0.
So it'd be easy to stand in the middle?
Easy to stand in the middle. The further up you get, the harder it's going to be.
You get dizzy though, probably.
Oh yeah, you get dizzy because you're spinning around and around. In fact, the dizziness part would probably be worse in the middle because you're actually just turning around and around as opposed to going around the center. Okay? So, yeah, if you're at the center, you don't have to hold on at all. You'll just stay there. Okay? But if you're out here at the very edge, you'll have to hold on really hard, okay? Because you're moving the fastest and thus have the most desire to leave the circle tangent to the circle. Okay, now yesterday I kind of mentioned some examples here, and I'll go over a few of those in a minute, but I'm going to use this example right here because it's kind of time appropriate. Okay? It doesn't matter whether I teach this lesson first semester or second semester, it's always around the time you're either getting your winter tires on or getting them off. Okay? How many people have 2 sets of tires? You should totally have 2 sets of tires. Okay? Winter tires make a big difference. Okay? They're much, much safer than summer tires. We talked about this in the friction lesson, right? They're softer. All right. When they put tires on a rim, they have to balance them. Okay? If they don't, maybe you've been in a car that does this. At certain speeds, the car just starts to shake. Okay? You slow down, the shake goes away. You get back to that speed, and the shake comes back. Okay? That is caused by a tire being out of balance. Lots of things can cause that. Okay? In the wintertime, it can be a chunk of snow is actually stuck to the inside of the rim. And there's extra mass on that part of the rim. Okay? Having extra mass on that part of the rim gives that part of the rim more inertia than the other side. And so when your tire goes around and around the circle, instead of going nice and smooth, the extra inertia makes that part of the tire want to leave the circle more than the other side, so the tire chatters up and down. Okay? And you have to get over to this side of the road and then try and reach in there and get the ice out. Okay? With the way tires are built, this also happens because a tire is made by pouring liquid rubber into a mold, closing the mold, cooling it, and then pulling the finished tire out. That doesn't always distribute the rubber perfectly. Okay? And over the course of time, things happen. You hit a curb, you know, stuff like that. Your rim isn't going to be perfectly machined anymore. Okay? And so the tire shop has to balance your tire so that it doesn't chatter. Okay? So what they do is they put it on this tire balancing machine and they spin it. And the tire balancing machine is on a spring, so it can detect when the tire starts to chatter, and from that, it can tell where the tire is heavier. And it'll tell them to put a weight on the other side of the rim. So you might see these on your tire. They come in 2 different forms. Okay? So if this is your rim, okay, and this is the tire on the outside, you might see a little tab on the outside, okay? A little metal tab. That's just a weight that they use to balance the tire. They don't use those as much now. Usually what they do is they put these little sticky squares, little square weights on the inside of the rim. Okay? And that offsets any imperfections in the tire or the wheel, okay? And then your tires won't chatter. If you bend your wheel or you take a chunk out of it by hitting a curb, it may become impossible to balance. Okay? And then you'd have to get it replaced. Okay? So this all works on this idea, though, of centripetal speed. Okay? The faster you go, the more centripetal force is required, the more inertia there is, okay? And you get that happening. But it only happens at certain resonant frequencies or resonant periods. That is, when the tire takes a certain amount of time to go around, it may or may not chatter. Okay? So if you're going along and you're going 70 kilometers an hour, the car's nice and smooth. All of a sudden, as you approach 80, the car's shaking violently. Okay? Slow down to 78, you're good again, okay? Because you're not at that resonant period or frequency.
So now, wait, since it was chattering at 80, what would happen if you're going like 120 then?
It'll be resonant, so at 120, it'll come back. So there'll be speeds at which it happens, not just one speed. There will be resonant speeds at which it will happen. Yeah. Okay, or resonant frequencies. We'll learn more about resonance in unit
So if you got to like going really fast, it would stop chattering?
No, well, I mean, it would go away, but then if you got to the next resonant frequency, it would come back again. And the faster you go, the more obvious it is. Okay, so if it resonates at 40, you'll notice a little. At 80, you'll notice it a bit more. At 120, you'll have trouble controlling the car. All right, is that making sense? Okay, so kind of real world application. All right, so let's look at this problem here. So the wheel of the car we're looking at has a radius of 0.29 meters. Okay, and it's being rotated at 830 revolutions per minute. Okay, did they give me a frequency or a period? It's a frequency. It's cycles per minute. If it was period, it would be minutes per cycle. Okay? Now, we don't want it in minutes. Nobody measures anything in minutes. So how do we get this into revolutions per second? Divided by 60, because it'll rotate less times in a second than it does in a minute, right? Okay, so we'll go that 830 and we'll divide that by 60, and that'll get us the frequency in cycles per second, okay? Which is probably what we want. Otherwise, we're going to get a speed of meters per minute, which, I mean, that's not really something we're going to understand, okay? All right, so 830 divided by 60. All right, so we're looking at 13.83 hertz, okay, or revolutions per second. Okay, we want to determine the speed at which the outer edge of the tire is moving. Okay, now the formula we got yesterday says that V equals 2 pi r over t. Okay, and I also told you that t equals 1 over f. Okay, so I have f and I have r. Okay, can I plug f into that formula? I can actually, okay, and it's because of this relationship. Period and frequency are the inverse of each other. Right now, this formula is really saying 2 times pi times r times 1 over t. Okay, well, if t is 1 over f, the opposite is true. F equals 1 over t. If I'm already multiplying by 1 over t, can I just plug the frequency number in there? I can. Okay, so this formula can come in kind of 2 forms. It can look like this as well, 2 pi r f. Now, if you don't want to remember that, that's fine. You could just go 1 over f, get t, and plug it into that original formula. It's going to work just fine. Okay, but sometimes it's good to understand the shortcuts too. Okay, all right. So I'm going to calculate the speed at which this tire machine is rotating. Okay, so 2, and always use pi. Use the pi button on your calculator when you're doing anything in this unit. Don't type in 3.14. Okay, we need all the other numbers. I know some of you know them to like really, really far. Okay, but just type in the pi button. Okay, 2 times pi times was 0.29, right? Okay, and then times f, which was that number. Okay, so the tire machine is spinning the tire at 25 meters per second, or 90 kilometers per hour. Okay, which is about what they do. Okay, they actually run it up, okay, so that they can detect where that chatter is happening, okay, but it generally tops out around 90. Not safe really to have it go much faster than that. Okay, everybody following what we did there? Is that going to be a terribly difficult formula to use? All right, so this is what we just did. Okay, so we got 25 meters per second. Now, understanding that circular motion says that the magnitude of the velocity vector is constant, that is, its speed is constant, but the vector is always changing.
Do you ever have a question where we would have to worry about pi being a significant digit?
No, because pi is not a measured value.
It doesn't have an end.
Yeah, it doesn't have an end. It's what is it, an irrational number? Okay. Okay. Yeah, so it's not a measured value. You can't measure pi. You can calculate it, but you can't measure it, right? It's always the quotient of circumference and radius. Okay. All right, so it's equally significant that the direction is not constant, and remember that any change in velocity, even if it's only a change in direction, means that acceleration is occurring. Okay, and in order to provide acceleration, you must provide a force. Okay, now the example that we used yesterday was David and Goliath. Okay, a sling is basically just something that allows you to multiply the force that you can exert. Okay? What's the maximum speed you could, let's say, theoretically throw a rock? Anybody know? Like a major league baseball pitcher can throw a baseball at about 160 kilometers an hour, 100 miles an hour. Okay? So, you know, that's fast. The average person's probably not going to throw that fast. Certainly a 14 or 15-year-old kid is probably not going to throw a rock, especially back in the time of, you know, Judea, David. Okay, like people were smaller and bigger. Okay, at that time, he's not throwing a rock at 160 kilometers an hour. Okay, but when he uses a sling, a little kid, okay, can make a rock go fast enough that it can cause a skull fracture. Okay, now that would mean the rock would be moving 280 to 300 meters per second, close to the speed of sound. Okay? In fact, the end of the sling, I think I told you this yesterday, breaks the sound barrier when you let it go. Okay, it'll actually crack. Okay? That cracking sound, or the cracking sound of a whip, okay, is actually the breaking the sound barrier. Okay? And you can do that pretty easily if you have things that are fairly long and fairly light. I don't know if this is strong enough. Okay, you hear the snap? Oh, it's a little snap because this isn't very big. Okay, but this can happen with all kinds of things. Whips would be a prime example. Okay, in the summer when I guide fly fishing, if I come across people who are not casting very well, I can hear the same thing happening. Okay, when they're whipping their rod back and forth, I can hear the snap at each end of their cast, and that's actually the fly breaking the sound barrier. And then I usually point out to them that the fly is messed up now, because breaking the sound barrier is hard on things. Okay, and so yeah, you can easily make something move that fast if you can lengthen the lever that you're using. Okay, putting a sling on the end of your arm lengthens your arm essentially and allows you to multiply the force you can exert. Okay, so I'm going to show you how it works. All right, so here's what we need to know about centripetal acceleration. Where is it always directed? Towards the center. Centripetal means center seeking. Anything centripetal, towards the center. Okay? Now, that's important because that's really about our only vector in this unit. Okay? Very rarely will a question ask you to put a vector on centripetal force, because by definition, centripetal means towards the center. Okay? Then you're going to get the odd question where it'll say give the magnitude and direction. Well, if it's centripetal, it's just towards the center. It's a no-brainer. Okay? Very rarely do we have anything other than that, except when we get into vertical, where you could have into the circle or out of the circle. Okay? And that would basically be gravity pulling out of the circle. All right, so the magnitude of the centripetal acceleration depends on two things: speed and radius. Okay? The bigger the circle, the smaller the centripetal acceleration. The faster you go, the greater the centripetal acceleration. Exponentially, because as you can see in this formula, V is squared. Okay, so if you've ever watched any racing, or if you have that crazy friend that takes corners too fast, okay? If you want to get around a corner without skidding, or let's say even this on-ramp over here, okay? Which lane can you go faster in, the inside or the outside? Outside. Always go faster than the outside. Not saying you need to try, you don't need to prove it or anything like that. I'll tell you right now it's true. Okay? The outside lane, faster. Because what's bigger in the outside lane? Radius. Okay? And if we're calculating your centripetal acceleration, a bigger radius means a lower centripetal acceleration. This is why race car drivers always take corners as wide as possible, okay? If they want to go as fast as possible. They want to pass somebody, okay, then they kind of change their arc, okay? But for a race car driver, if they just follow that's weird. If they just follow this circle, that can make that corner difficult. So what you'll often see them do is they'll come towards the outside of the track, and then they'll cut in like this and go wide. That's supposed to be circular. Does that have a wider radius than just going around the inside of the corner? Yeah, that's why they do that. Okay? It makes them able to take those corners at a higher rate of speed. Now, if they want to pass somebody, then that's where it gets tricky, and that's where skill becomes involved, because you got to get outside, and then you got to cut in a little bit and try and take that corner on the inside. Or sometimes they pass on the outside. Okay? All right. Making sense there. But the thing to remember here is that speed has an exponential relationship. So if I double my speed, my centripetal acceleration is going to have to be 4 times greater. Okay? And that centripetal acceleration has to be provided by a centripetal force. If we're talking about going around a corner, the centripetal force is provided by friction. And there aren't too many situations where you can just suddenly magically get 4 times as much friction out of the same situation. Tires and road. Okay? If you double your speed, you better hang on, because you're probably not going to do very well there. Because you're now going to be relying on or hoping that you actually have 4 times the amount of friction you're supposed to have. Okay? That's probably not true. Okay? Everybody with me on that? Okay? This is something we always have to consider in the wintertime. Right? When it first snows or first gets icy, okay, people go to turn a corner and what happens? Okay? Like it happened this winter, right? The guy ended up in the drink over there, okay, in the little settling pond.
Keep going straight.
Okay? Yeah, you just keep going straight. Okay? There wasn't enough friction for him to take that corner at the speed he was going. Okay? So he obeyed Newton's first law. Straight line, right into the pond. Okay? So how do we fix that? Well, we put sand or something down and maybe try and change the amount of friction that's available, or go slower. That one will always work. Going slower will always work. Okay? Because then there might be enough friction. Okay? But it doesn't take much. Okay? We've all been in that situation where it's just over the amount that friction can provide. And then suddenly you're going straight. And what's our natural reaction? Hit the brakes and crank the wheel. The two things that are the worst things to do in that situation, but they're our gut instinct. Okay? Is to go, oh crap, turn harder, brake, slow down, and that is not going to work. Both of those things reduce the amount of friction that's available to you. Okay? So what you want to do is back off the brake and turn a little wider. So you can reduce R. Okay? And then maybe you'll have enough friction to make the corner. It's actually funny. Anybody ever watch like Canada or America's Worst Driver? They always have that test on there, okay, where they have like the simulated icy corner, okay, and they take off the anti-lock, they take the chip out of the anti-lock brakes so that they can't use them, and then they try and take the corner, and they always go through the styrofoam blocks, okay, because they do exactly that thing. They pound on the brakes, they crank the wheel, and they go straight, okay, instead of, I'm not on the brakes very hard, I can feel the skid coming, so I back off the brakes, I turn a little bit wider. Yeah, you're gonna go out wide, but you might not hit the wall. Okay? It's very counterintuitive, right? But it's true. All right. So, centripetal acceleration is a vector quantity, obviously, towards the center. Okay? And it's true for anything moving in a circle, including the moon orbiting the Earth. Okay? Gravity provides the centripetal force in that situation. Okay? But the moon is always accelerating towards the Earth. Okay? And the same is true for satellites, like the International Space Station. Okay? When you're on the International Space Station, how do you feel? When they're on the International Space Station, they are weightless. Well, they're not really weightless. They still have weight, but they're apparently weightless. Okay? And the reason they feel weightless is because they're always falling, always accelerating towards the center of the Earth. Okay? It's so weird, but it's because they're going in a circle, okay? They're going fast enough that they don't get any closer to the Earth. They accelerate towards the Earth, but they don't get any closer to it. That's how an orbit is achieved, okay? And that's why they feel weightless.
In like zero gravity, would that swing thing work or no?
Yeah.
Like, so you can still throw stuff in space and it's still.
Oh yeah. It's just, you have to brace yourself.
Ah,
Newton's third law is not your friend in space.
right.
Okay, like this is one of the things, they actually do a good job of this in science fiction movies, fighting a fire with a fire extinguisher in zero gravity. We saw what happened with Wall-E, right? So imagine you're trying to fight a fire in zero gravity and you just squeeze the trigger on the fire extinguisher. You're gonna shoot right back, okay, and hit the wall, right? So what you have to do is you have to brace yourself so that you got something that'll push back against that force. Throwing is the same thing. If I throw something, I accelerate it this way by pushing it, it pushes back on me and I tumble and cartwheel back the other way. So with that sling, right, sure, I'm pulling it back towards the center, but as soon as I let it go, there's gonna be a reaction force on me that's gonna cause me to move too. Okay. That's why there's so much training for astronauts. Moving in zero gravity is a totally different experience. Okay, we'll actually talk about that one a little bit later in the unit when we do artificial gravity. All right, so what's going on here for anything to move in a circle, okay, is yes, we've got that net force pulling towards the middle. We've got the desire, the inertia of the object wanting to go in a straight line, okay, but we're pulled towards the center object, okay, and that's true at any point in the circle. The velocity vector is always tangent, okay, but we're always accelerating towards the center. Okay? So it basically just ends up being I'm always falling, but I'm moving this way, but I'm always falling, and I'm moving this way, and it ends up making a circle or an orbit. Okay. Okay. So an object that has uniform motion would fly off on a tangent line, okay, if suddenly released from the circular path. Okay, and that's what we saw with David and Goliath there, okay? And so the object is always accelerating towards the center of the circle, okay? And centripetal means center seeking. Okay. Are you all right with that idea? So let's have a look at this, okay? So tight turns and gentle turns. So we're gonna look at the effect of radius on centripetal acceleration. Okay, so I've got this first corner that has a radius of 320 meters, and then I've got this corner that has a radius of 960 meters, so 3 times the radius. Okay, so in both cases, we're moving at a velocity of 28 meters per second. All right, so for this first one, the centripetal acceleration would be v squared over r, so that would be 28 squared divided by 320. Okay, so we'd experience an acceleration of 2.45 meters per second squared. So if this was you in your crazy friend's car, okay, you would be like face mashed up against the window, okay, holding on to the holy crap bar for dear life, okay, and you would feel the window push on your face with a force of about 1/4 of your usual weight. Okay, because that's about 1/4 of gravity. Okay, so you'd feel that force. Now, this is where you don't want to be in one of those Jeeps without doors. Okay, well, I mean, you're wearing your seatbelt, obviously. Okay, but if you weren't wearing your seatbelt and you're in a Jeep without doors, you are going to exit the vehicle. Okay, in a straight line. Okay, and that's not going to be good. Okay. Now, if we take that corner, still crazy friend, 28 meters per second, okay, but now that corner is wider, 3 times wider, okay, our centripetal acceleration is going to be how many times smaller? If I'm dividing by a number 3 times as large, I'm going to end up with a number 3 times smaller. Yeah, okay, and so that's going to be 960 on this one. Okay, pretty sure if I multiply that by 3, I get 2.45. Okay, so 3 times less, okay, because I took a corner 3 times wider. Okay, what are some things we do to make corners easier to take? Devlin did this. He made the banked corner sign. Okay, that's what we call that. Okay, we simply bank the curve. Every exit ramp you've ever taken is a banked curve. Okay, we don't make them flat, because if they're flat, you can only rely on friction to hold you in the corner. If you bank the corner, you use Newton's third law a little bit. Okay, so if the corner is banked and you're going around the corner, it's an inclined plane, and you're sitting on it. And as you go around, you push on the corner. And the faster you go, the harder you push on that corner. Okay? And so the corner has to push back. Now, this is the kind of weird thing about it, but at the angle of bank, the force of the corner is not straight towards the center, it's perpendicular to the surface. Okay? But because it's angled, it has a component that is directed back towards the center of the circle. Okay? That's why banked corners work. Okay? We bank corners because it makes them safer. Okay? And we can guarantee a speed at which they will be safe regardless of the road conditions. Okay? So if you see the recommended speed for a banked corner, that's the speed to take it at right after freezing rain when there's essentially no friction. Okay? If you go faster than that, you'll slide out. If you go slower than that, you'll slide in. Okay? I've seen it happen. Okay? An overcautious driver in front of me after freezing rain, going around the corner, and they went too slow, and they slid in. I had to go out and around them because I knew what was gonna happen. And I'm like, oh crap, because I could feel my truck starting to slide. Gotta speed up. And sped up a little bit and had to go around them as they slid into the center. Okay? Sometimes being overcautious is bad too. And now, crazy road conditions, it was super slippery. And most of the time you don't have to worry about that, but there's gonna be a guaranteed safe speed when you bank the corner. Okay? It's also how planes turn. Okay? A plane doesn't just do this, wings level to turn. Okay? If they wanna turn, they do this. By banking their wings, the lift the wings produces has a component that is horizontal and directed towards the center. Okay? Now, at the same time, if you tilt your wings in a plane like this, you're gonna turn, but you're also going to fall, yeah, because when your wings are flat, you produce enough lift to stay level. If you go like this, now their lift is not directly up. It has an upward component, but it might not be enough, and the plane will drop. That's actually how planes lose altitude when they're approaching a runway. Okay, they'll almost always circle a little bit, and during that circle, they'll drop. If a fighter aircraft goes like this and stands on its edge, it can take a corner, but it's also dropping like a rock. Okay, because there's no lift anymore. Okay, and it's actually falling. Something they didn't really show well in Top Gun. Okay, I'm gonna give you guys about oh, sorry, no, we gotta do the speed one here. Nope, we don't. We already talked about it, so we're not doing it. Okay, I'm gonna give you guys about a 5-minute break, and then we're gonna talk about centripetal force here. Okay, so continuing on from what we just talked about, okay, we were just talking about that centripetal acceleration is v squared over r. Okay, now Newton's second law says that net force is mass times acceleration. Okay, and we said that the centripetal force is going to be the net force in this unit. Okay, so would we then say that centripetal force equals mass times centripetal acceleration? Could that be true? It is true. Okay, it's still Newton's second law. Okay, the sum of all forces has to be directed towards the center, or the object's not going to move towards the center. Okay, now if I substitute in this formula here for centripetal acceleration, I get this: mv squared over r. Okay, that is going to be our m times a for this unit. Okay, we will use that formula, Fc equals mv squared over r, as much as we use m times a in unit 3. Okay, it's going to govern everything we do here. All right, so centripetal force is dependent on mass, speed, and radius. Okay, but which one of those things has the biggest effect? Speed, because speed is squared, right? It has an exponential relationship. Okay.
Okay, so circular motion cannot occur without a force pulling towards the center. Lots of forces can act as centripetal forces. We've already talked about gravity. We've talked about friction. Okay, when we're talking about banked curves, we're talking about normal force. Okay, lots of forces can act as a centripetal force. Tension in a string. Okay, when I'm whirling around the circular motion demo there. Okay, lots of things can act as centripetal forces, but sometimes it's not something we can necessarily see. Okay, like we don't necessarily notice that friction is what keeps you in a corner. Okay, we don't see that gravity is what keeps the moon in orbit around the Earth. Okay, because we can't see that connection. When I'm whirling something around the circle, the string is there, it's obvious. Okay, but sometimes looking at a situation, it's a little tougher to figure out why that object is moving in a circle or what's providing the force back towards the center. Okay. So learn how centripetal forces will operate and look at banked curves and how they use Newton's third law to produce greater centripetal force. Okay, it's not by accident that racetracks have very highly banked curves. If you've ever watched any NASCAR, okay, those curves are banked so steeply that they actually have to use a crane to keep the paving machines from falling down the hill when they pave the corners. Okay, so because the normal paving machine that you might see out here, it just sits flat and dumps the pavement and then they pack it down. Well, the packers and the pavement thing, okay, they'll tip over on a banked curve like a NASCAR track. So we actually have a crane on the outside of the track that comes over and pulls them back against the corner to keep them there. Otherwise they would fall down. Okay, all right, so that's what we're going to be looking at for this one. Okay. So Newton's second law indicates that whenever an object accelerates, there's a net force. Okay, that's true for circles as well. Okay, and this is what we just talked about a minute ago. Centripetal force is net force, it's mass times centripetal acceleration, which is mv squared over r. Okay, that formula is on your formula sheet, so you don't have to worry about memorizing it. Okay, but it is the one that we're going to use most often. Okay, so the net force is the centripetal force. Okay, and as I was saying before, in some cases it's easy to tell what that centripetal force is, okay, because you can actually see the direct connection between the object and the center of the circle, okay, but other times it's not as obvious, okay, and so we have to be a bit more observant, okay, or calculating in those situations. Now, back in Unit 2, we always said this. F net is m times a, but it's also the vector sum of all forces. Okay, is this part still true if we're talking about centripetal force? Yeah, it is. Okay, you just aren't going to have a lot of forces going anywhere other than the center of the circle until we get to vertical circular motion. Okay, and vertical circular motion works a little bit different. Okay, with uniform circular motion, so horizontal, okay, the speed stays constant. Okay, there's no force trying to pull this thing directly out of the circle. Okay, there's no centrifugal force. But as soon as that circle becomes vertical, okay, what happens to the speed of the?
It's faster when it's falling.
It's faster on the bottom, faster when it's falling. Okay, because on the bottom, gravity is actually trying to pull it out of the circle. Okay, and the string is pulling up, yeah, or into the circle, right? It's up is still true, okay? But that's into the circle, okay? So in actuality, the force is always changing in a circle like this because the speed's always changing, okay? And when you get to the top of the circle, which way does the gravity pull now? Down, which it now happens to be into the center, okay? Once at the bottom, gravity's acting out. Once at the top, gravity's acting in, okay? So we kind of have to look at it and go, okay, what forces are acting and which direction are they going? So sum of all forces is still a thing here, just not so much for uniform circular motion. All right, so the model airplane, okay, as an example here, okay, has the centripetal force provided by the string, or my tape had the centripetal force supplied by the string. Okay, inertia wants you to go this way. There really isn't any center fleeing force, but we use that term incorrectly all the time. Okay, like for example, in a centrifuge, okay, which is a medical instrument that they use to basically separate the components of blood. Okay, so if you get a blood test Okay, what they'll do is they'll put that vial lots of times in a centrifuge and they'll whirl it around so all the heavy elements, that would be the cells, go to the bottom and all the plasma and lighter stuff stays on the top because it has less inertia. Okay, same thing is done, if you've ever watched anything like CSI or anything like that, when they get a DNA sample, okay, they put them in the centrifuge and they spin them around so all the heavy cellular components and DNA will end up at the bottom of the vial and then they stick that fancy little pipette thing in there and take it out. Okay, it's not using centrifugal force. It's actually using inertia and centripetal force, okay? It's the bottom of the vial that actually pushes back towards the center and keeps the material in there. Okay, everybody all right with that idea? Okay. All right, so there really isn't such a thing as centrifugal force. It is really just inertia, okay? It feels like you want to go out of the circle, but you're actually trying to go tangent to the circle, okay, when you're feeling that force, okay? How many people have ever ridden the Gravitron? They usually have it at Stampede.
Is that thing that spins? And
Yeah.
goes,
Yeah, it spins and you get stuck to the wall and you can actually like stand on the wall like this and you won't fall down because it's spinning so fast that your inertia, desire to leave the circle, is greater than gravity's ability to pull you directly downward. Okay, so it's actually how we generate artificial gravity as well. You've seen like The Martian and movies like that, okay, which we'll talk about later. All right, so, show you here kind of what I mean by that. Okay, so that's kind of how all of those kind of rides work, and you can make some if you make them totally vertical, they like a Ferris wheel even, whereas you're going over the top, you feel weightless, and then you feel heavy on the bottom.
If you were on the one without the roof and it was at a 90-degree angle, when you're facing face down, would you still be pushed up or would you fall?
Yes, as long as you're going fast enough. When we get to vertical circles, it'll make more sense, but there's a minimum speed you have to achieve to move in a vertical circle. Like, if I whirl this thing around in a vertical circle really fast, no problem, right? Like it's gonna stay in the circle, but if I slow it down, right, there's a minimum speed that I have to achieve, otherwise it falls instead of staying in the circle. Now, if you watch the string, when I get to that minimum speed, or I'm right around it, there's actually no tension in the string. So how would you feel? Very light or
like you're falling.
or yeah, weightless. Yeah, you can actually make a feeling of apparent weightlessness at the top. Okay? And the faster you go, the heavier you feel at the bottom. Okay? But there's a minimum speed. If you're just at that minimum speed, okay, you would feel weightless at the top. Not too many rides will do that because it's not super safe. If something were to happen where they went a little bit slower, you could fall out. That's generally bad. Well, yeah, I mean, you always got a safety strap, but like, you don't want the ride that, and people are stuck at the top looking down, it's not fun.
I mean, I'm not gonna try it, but I'm sure someone.
Someone will. Okay, so looking at speed here, guys, the effect of speed on centripetal force. Okay, we know it's exponential by looking at the formula, but sometimes it's helpful to kind of just prove that. Okay, so we want to find out what's the tension in the string, or the centripetal force, for speeds of 19 and 38. 38 is twice as much as 19. Okay, so FC equals mv squared over r. Okay, so we'd have the mass is 0.9 kilograms times 19 squared, okay, divided by 17 meters. 0.9 times 19 squared, okay, divided by 17. All right, so we would need a centripetal force there of 19 newtons. But if I double that speed, now I need 4 times as much centripetal force. Okay, everybody all right with that? Okay, so it's that exponential relationship again. If I double the speed, okay, I'm gonna have to hold on to that string 4 times as hard, okay, or it's gonna wanna go. All right, everybody okay with that idea?
Is it still in newtons?
Yeah, still in newtons. Yeah, force is always gonna be in newtons. Okay, what about radius? So if I start out with an 11-meter radius and whirl it at 28, and then I go to 22, how's the force going to change?
It's gonna double.
It's gonna be double in which situation? The 11 or the 22?
The 22.
The 11.
In the 11, okay?
Oh,
So small radius, okay, I gotta hold on to it pretty hard, okay? Large radius at that same speed, it's nothing, right? That I hardly have to hold on to it at all, okay? So because we're dividing by r, any increase in r is gonna make FC go down linearly, okay? So it'll be an inversely linear or inversely proportional relationship there, okay? So we'd have, okay, first situation here, 0.9 kilograms times 28 squared divided by 11, a radius of 11 meters. Okay, so 0.9 times 28 squared divided by 11, and we get 64, right? If we do that with a 22 meter one, okay, whoops, I squared the 22. Okay, I get half of 64, 32, right? Exactly as you thought we would get. Okay, everybody's all right with that? It's just important to know those relationships because sometimes you get a multiple choice question that kind of asks about what kind of things can affect centripetal force, how they might affect centripetal force. Okay, we know taking a corner wider makes it easier. That's why the radius has an inverse relationship. We know that going faster makes the corner harder to take because speed has an exponential relationship with that centripetal force. Okay. Okay, so this is what we were talking about here when we're talking about curves. Okay, these are what we call unbanked curves, so they're leveled. Okay, on a level curve, what keeps you in the corner? Friction. Yeah, friction acts as your centripetal force when you go around an unbanked corner. Friction between your tires and the road is what keeps you from going off in a straight line. If it's icy, it's easy to go off in a straight line, okay, because that friction is not sufficient to keep you in that corner. Okay, so I want to rely on static frictional force. I don't want my tires to slide. Okay, if my tires start to slide, that's when I'm in trouble. Okay, then I'm relying on kinetic friction, which we know is always less than static friction. Okay, so I want static frictional force. I want to go around that corner. That will allow me to negotiate the corner as fast as possible. Okay, so if that's true, if not sliding or spinning makes you go around the corner fastest, why do people drift corners?
Because they think it's faster.
And it's more fun.
And it's more
And it looks way cooler. Okay? But in terms of speed, in terms of being able to go around a corner faster, static friction is always faster. Okay? Drifting just looks way cooler. Okay? Now, when you're drifting a corner, you still go around the corner, but you change what forces you use to do that. Okay? Instead of just having static frictional force pointed directly towards the center, you now angle the car. Okay? So it's not going this way, tangent to the circle. It's now pointing like this. Not quite towards the center, but a little more towards the center. And what are your back wheels doing? They're spinning. They're providing a force, okay, that's this way. Okay, now it would have a component that would act towards the center, okay, but it's not going to be great. Okay? And you're relying a lot on your initial inertia as you approach that corner, right? Because to drift a corner, you got to pull the handbrake to start the skid, then let the handbrake off and power on, okay, and get the back wheels really, really turning. Okay, so that you are providing that force to slide around the corner. Okay, always directed a little bit towards the center. Okay, now a drifting car may actually be able to do this part of the corner as fast, or maybe even a little bit faster than someone going around this way. But the disadvantage for the drifter is when they get to this point on the corner. Someone who takes the corner without their tires spinning can now hit the gas, and all of their power points forward. And their tires are locked up, so they're going to get all of that power to the road. If you've been spinning your tires all the way around the corner, when you get to this point where the straight is and you want to power down the straight,
you actually have to back off the gas to allow your tires to regain traction. And then you can accelerate. So it's actually coming out of the corner where the person using static friction is going to have the advantage. They can accelerate out of that corner better than someone who's initiated a skid on purpose. Okay, so you've got to let those wheels lock up again. Okay, that sort of making sense? All right, now, if we're looking at that, okay, this is the thing I was telling you we were going to do all the time, okay? FC is our net force, which is the vector sum of all forces. The force keeping me in the corner is friction. Okay? So my centripetal force is being provided by friction, which means friction is the centripetal force. So this would be my vector sum of all forces. Pretty easy, it's just one force. Okay? And then I'd set the formulas. Then I'd set the formulas equal to each other. Now, because the corner is not banked, so it's level, normal force is equal to what force? Gravity. Okay, so I end up with that. mv squared over r equals mu mg. If I do any manipulating here, what happens to m? It cancels. So mass doesn't matter?
Not in this situation.
Not in this situation. Okay, I mean, think about all the corners you've gone around, especially the bank corners. Okay, I mean, they're a little bit different, but in this way, mass cancels on them too. You ever see different speed limits for different size vehicles? You did? That would require a lot of signage, right? If mass made a difference for how fast you could take a corner, every mass would have a different speed limit. Okay? So if I manipulate this for V, right, I'd multiply both sides by R, M would cancel, and I'd be left with this. V is the square root of the coefficient of friction times gravity times radius. Mass doesn't even factor in there. Okay, now, it's never that simple, obviously. Bigger vehicles also tend to be a bit taller, which can give them a tipping ability that a lower car wouldn't have. You never see a tall sports car. Okay, they're always low to the ground so that they don't have any roll. Okay, if you try and take a corner in a big cube van, okay, you're going to tip over. Most trucks and SUVs have the warning on the back of the visor saying this car will tip over if you go too fast. Okay, but in actual fact, your mass doesn't make any difference for how fast you can take a corner. Okay? It's just dependent on the coefficient of friction and the radius. Okay, we will talk more about that tomorrow. You will not have a quiz tomorrow. We haven't gone over enough stuff.